I want to show a few labs that we do with standing waves. So I'm going to start out with this string. We're going to have a standing transverse wave on this string, and we've got a vibrator back here. If I crank it on, what I want to do is I want to start at a pretty low frequency. And this is vibrating back and forth, and you can see there's no real standing wave setting up. It's just kind of random stuff canceling out until I get to a certain frequency, and then you can see it start to get a little more interesting. And then you're starting to get that first harmonic. And I wanted to get that first harmonic. What I really want is the biggest one loop amplitude. But another thing is, when I find that first harmonic, it should be a really, I'll call it a happy resonance. See, here it got a little quieter. So that would probably be pretty good first harmonic right there. Big amplitude from the center to the top. Ooh, that might even be better. And it got really quiet. That means that vibrator's not fighting it as much. So you have a pretty good first harmonic wave there. Okay? Then I can go up to higher harmonics by going up. And we know for standing waves on a string, the higher harmonics are multiples of the fundamental. So I know that was about 11. So if I go up to about 22, I should find a second harmonic. And here it comes. Oh, I got it a little bigger. And if I get a really nice frequency, it'll probably get a little quieter. See, it's getting a little quieter. The fundamental was a little less than 22. And I would say the second harmonic right about here is, I'm sorry, the fundamental was a little less than 11. So twice that should be where the second harmonic is. And I think I might have passed it. It was a little under 22. Okay, that's actually not bad. Maybe it's a little higher than 22. That's probably pretty good, 22.4. So I'd expect the third harmonic to be up about 33. Let's go check. And there it is. I'm at about 33 hertz. 3 times the fundamental, 33.9, seems to be the third harmonic. Okay, and you can see 1, 2, 3 loops. Okay, and the way we generally use this is if I know that frequency 33.9, if I measure the string length, and I'm going to do a really, really rough job of that. If I measure the string length, about 69 centimeters, 0.69 meters. So what that means is 0.69 meters is 1, 2, 3 half wavelengths. 3 times lambda over 4 equals 0.69. Okay? And so we can find the wavelength from that. 3 half, oh, I had over 4, over 2. 3 half wavelengths is 0.69. Let me shut it off. So a full wavelength would be 1.34 divided by 3. Actually, it was 23 times 2. It ends up being 46. 0.46 meters is the wavelength, just solving that. And if I knew the frequency was 33.9, I think I said, frequency is 33.9 hertz, I could find the velocity, F times lambda. Now, if I really want to find the speed of the waves on there, I'd want to do that for a whole bunch of different wavelengths and a whole bunch of different harmonics. Okay? And one thing we can do on that is V equals F lambda. One way of averaging, you could just average the velocities, or you could, to find this, what we could do is we could say V times 1 over F equals lambda. So we could plot lambda on the y-axis and 1 over F, 1 over the frequency on the x-axis, and the slope will be v, if we think of y equals mx. If you're not used to linearizations, don't worry about this, but that's one way of finding. Okay, now what I want to do is show you that a variety of this kind of lab is actually talking about the tension. And the tension in the string, the velocity is equal to square root of the tension over the density. And density, I'll put mass per unit length. It's the linear density. So the tension divided by the density gives you the velocity. So what we can do is we can change the tension, see how the velocity changes, and we could figure out the density of the string. And that's another one where you could do linearization to solve that. But let me just show you the basic setup for doing that. This is kind of a standard physics standing wave lab. What we do is we need to know the tension. So there are a couple of ways to do it. You could use a force sensor or a spring scale, and you can loosen that up. And then you could measure, there's 1.5 newtons. I read it on the spring scale. And then I lock that in, but it won't work because my screw has come loose. So you lock that in, and that's not going to work. You lock that in, and then you know the tension. Another way of doing it is to hang a known mass off, make sure that the tension's the same on both sides, make sure it can move freely. And then if I know mg and it's in equilibrium, then I know the tension and I know that tension. So what you can do is do a variety of masses, have a variety of tensions, and take data just using the approach we had for tension and velocity, seeing how the tension affects the velocity. And if you then use the equation v equals square root of tension over the density, you can actually solve for the density. Usually this is done with like a linearization approach, where you graph two variables so you can find the density. If you don't understand linearization, again, no big deal, but that's the basic standing wave lab that tends to be done in AP physics and intensified physics. I want to show you now some longitudinal standing wave labs that are common. Generally what we have is some kind of tube, got a bunch of tubes here, and maybe you can block one of the ends of the tube. So you can do it open at both ends or closed at one end experiment. And I'll show you a couple of common ways. This is an expanding tube, and so I can slide this in and out and change the functional length of it. Now, if it's open at both ends, it ends up having two displacement nodes, one at each end, okay? Or displacement antinodes or pressure nodes. So we consider, in my classes, we consider the displacement node, antinodes, the parts that can move the most. So it goes from one antinode to the next antinode is the fundamental. Other ones would have more waves crammed in there, but the lowest frequency, longest wavelength that resonates in that size tube is the one that will be the fundamental, and that's the one that's going to dominate what we hear. So let's take a look at what that looks like. What I have to do is I actually have to generate an audio frequency, and sometimes they do it with tuning forks. Just so I don't have to fuss around on this lab, you could use a 540 hertz tuning fork for this one, which I don't happen to have, something that is in this range of this as a half wavelength. And you would hit the tuning fork and you would listen at the other end while you move. Clearly you need a whole lot more hands to do that. What I do is I play this audio function generator on a Vernier LabQuest, and I find the micro or the speaker. And what I do is I make it longer and shorter. And at some point I hear where it's loudest. And that's going to be where there's a resonance. Now obviously it's really hard to get a very, very good reading. But when I have done this, I have found that in this case, this ends up being about 0.28 meters. And there's actually, what's kind of weird with these antinodes, don't form exactly at the ends. There's this end correction for tubes that they would have to give you in a lab, what the size of that is, and it depends on the diameter of the tube. When I did it for this one, and I did my calculation for 540 hertz, remember that this is a half wavelength, is that tube length plus the end correction. So I got that number, which ended up being 0.318 meters, multiplied by 2, and I used this frequency and the wavelength, and I can calculate the speed of sound, 343, which seems pretty reasonable. But I'll tell you what, if I do that 5 times, I'm going to get some very, very different numbers. These don't end up being great ways to get exact speeds of sound. Okay, so there's one way, and that's closed, open, open. Another way you can do it is do closed at one end. Put a plug in there, and I'm going to adjust it with this. I'm just using this to push it. You can use a ruler. And what I'm going to do is, once again, I've played around with this enough that I found a good frequency that seems to work for this is 500 hertz. So I play the 500 hertz. This one's a little trickier. So now I've got to push and I've got to listen here, and it's hard to do. Okay, so I'm going to listen. For the resonance. I hope you're getting a good look at my bald head. You can see the problem. The problem is I may not recognize that it's a little louder until I'm past it. So this is very, very fussy. This takes so long to go back and forth and find out where did you think that best one was. When I did this carefully, what I found was the plug at 15 centimeters worked. So 15 centimeters plus the edge correction is a quarter wavelength. So when I include the end correction, I ended up with 0.169 as a quarter wavelength, as the length. So quarter wavelength is 0.169. I multiply by 4, I get my wavelength. Wavelength times the frequency ended up being about 338. So I was able to get a decent result with that also. Again, because speed of sound in the room should be somewhere between 343, 346 meters per second. Okay, the last one I'm going to do is with a glass of water and a tube. Okay, and for this one I used a 384 hertz tuning fork. Okay, here's what I'm going to do. Here's the drawing. I'm going to lower the tube into the water. Well, the water is going to form a closed end. So it's going to be another one of these quarter wavelength fundamentals. So as I lower it in, I'm going to listen. If I can get this right. There we go. And you can see it's a little easier because I can move it back and forth. It went whoa, whoa, as I moved it up and down, and I picked the loudest point close. I measured it. Okay, again, this is really not I'm not being very careful with my measurements. I'm just trying to demonstrate what this might look like. So you figure out how deep was that, and now from here to there, that length would be a closed tube where you had resonance. So I measure that, a little end correction. Again, you either have to get that from your lab instructor or from looking up how you do end correction as a function of the diameter. I add that onto the length and I multiply by 4 because this would be a quarter wavelength. A full wavelength would be 4 times that. And when I did that with a 384 hertz tuning fork, I ended up with 357 meters per second. Okay, so those are the 3 kinds of standard longitudinal or audio standing waves that we do in physics labs.